drainage system design. We're going to talk about runoff. We're going to talk about coefficient of runoff. What products are going to match up to the application that you're looking to address. So what we're going to be talking about here is design context considerations, runoff and surface type, design storms, stormwater calculations, and system design steps. So we're going to talk about capturing water, filtration, conveyance, detention, retention, and infiltration, and discharge and overflow. So whenever we talk about a drainage system design, we're going to be talking about the Federal Clean Water Act of 1972. So the EPA regulates stormwater pursuant to the CWA, and the goal is to restore all waters of the U.S. to fishable and swimmable conditions. This is why when we talk about stormwater regs, the overall goal of those regulations is to make sure that our streams and rivers are safe for people like you and I to fish in, to go swimming in, and not have to worry about getting sick. So state and local regulations, I mean, I'm sure many of you have come across tightening and raised regulations in terms of what you can do with stormwater on a property, having to keep it on the property, having to keep it out of municipal systems. We'll get into those reasons why here as we go through. But the best management practices are designed to reduce peak flows and non-point source pollution by encouraging detention, retention, infiltration, and filtration. So when we talk about that, when we do a design system, or when an engineer does a system design where, once there was woods and now there's a shopping mall or a parking lot, in a natural state, when rain falls, you get about 40% of that rain that's going to rise as evapotranspiration, 10% is going to run off, and the rest of the 50% is going to get absorbed back into the ground. Very little runoff in these sort of conditions. In an urban type environment, or where there's nothing but impervious surface, 30% of the water is going to evapotranspirate. 55% of that water is going to go away as a result of runoff, and you're only going to get about 15% of the water that's actually going to make it back down into the ground. So why are we worried about this? This is sort of what was an aha moment for me when I first started learning about all this. When I first came on here at NDS, a lot of the reason why we want to have these regulations in place is because the sewage system from your home and the sewage and the stormwater grates that you see outside of your house, on streets that collect stormwater running down along the curbs and into these grates, they all make their way at some point or another, especially here in the Northeast. If you look in the map, that basically coincides with older, larger cities. All your stormwater and your sewage ends up it's a one-point system. So that's all going to make it to one large pipe, which is going to make its way to a weir at the end of that pipe, where in normal conditions without a ton of stormwater runoff, those solids in the waste will collect in front of the weir and get pumped up to the wastewater treatment facility, pumped back out into the river. Now, when that gets inundated with stormwater, that pipe that you see, that main one at the bottom of the screen, that is going to get so filled, it's going to overwhelm the weir, and then all that raw sewage makes its way right into the river where we're trying to fish and swim and everything else. So the less water that makes it into the stormwater system, the safer the river is going to be, where that water is eventually going to make its way to. So when we're talking about runoff from surfaces, rainfall runs off at different surfaces at different rates. So something like a lawn is going to have a much higher coefficient, or a much lower coefficient of runoff than something like an impervious surface like a roof, a parking lot, a pool deck, or a driveway. So when we're talking about these things in terms of a formula, a number that we can plug into a larger formula to get a number that we can work with, we're talking about this coefficient of runoff. Coefficient of runoff is the percentage of runoff expected from established surface types, which is used in calculating peak flows for the given drainage areas. So if you look here on the left-hand side, the surface type asphalt pavement, 0.85 to 0.95. That means 85 to 95% of the rain that falls on an asphalt pavement will actually run off. Now, if you get down to a sandy soil, which is the far right all the way at the bottom, which will drain water the fastest, you're only at a 0.3%, which means that 30% of the water that falls is actually going to run off of that surface. So you can see there's a huge difference here. So coefficient of runoff is always going to be represented by the letter C in our rational formula, which we're going to be getting into here a little bit later. Design storms. So a design storm is a rainfall event with established intensity for a given location and frequency. Used in design stormwater drainage system to size components such as capture devices, conveyance, piping, and infiltration and retention detention systems. You know, we're talking about retention detention systems. We're talking about dry wells, infiltration trenches, dry wet ponds, chambers, so on and so forth. So where we are, if you look, you see where Pennsylvania is, southeastern Pennsylvania, the 25-year, 30-minute rainfall, which is pretty much a baseline that a lot of townships use. Always check with your municipality when you're designing one of these things to see what that design storm actually is. Some people want you to use a 1 hour, 10-year storm. Some townships want you to use a 25-year, 10-minute storm. Every one can be different. You just have to make sure that you line up with the design storm that the municipality that you're working in requires. It's going to take a little bit of homework on everybody's behalf to make sure that you get that number right. But a 25-year, 30-minute rainfall map is what you're looking at here, and that's sort of a good baseline to see what we're really going to be working with. If you look sort of in southeastern PA, kind of going across into Jersey, most of us are going to be in that 2 to, actually 1.75 to 2.25 circle. It's probably I'd go with a 2 or 2.25 inch per 30-minute rainfall as a sort of a worst case scenario to size your systems. When we get the app back up and running, you'll actually be able to get that down to a zip code. So it'll be very, very exact as to where you're working to come up with your design storm. So selecting a design storm for runoff calculations, we just sort of spoke about that. You have to make sure that you have the appropriate design storm, and it's always going to be applicable development guidance and regulations. So calculating peak runoff rate for capture and conveyance. We're going to be getting the water into the ground via capture device and then moving through a pipe. 25-year, 10-minute event is going to be a pretty good baseline for that. Now, if you're calculating runoff rate for detention and retention, they're going to see a 1-year, 60-minute event, which can be a very different number than a 25-year, 10-minute event. This is all very, very much simplified on the app, because everything will be, once you tap on the selections, you can choose the year, the duration, and you come up with these numbers really, really simply. So just to give you an example here, a 25-year, 10-minute event in Houston, Texas is going to come out to be about 2.0 inches per hour. In Richmond, this just shows you San Diego, Richmond, and Houston, how different those can actually be. So let me get back to that. All right. So when we're coming up with that calculation, we're going to be using the rational formula. So it's Q equals CIA. So Q being the designed peak runoff rate, that's the solution that you're looking for. The C being the runoff coefficient, the I being the rainfall intensity, and then the A being the drainage area in acres. These are all things that you can plug into that system in terms of square feet. There are a lot of different things that go into that. But when we get to the website portion, I can show you how to actually calculate these things. So when we're designing a system, the 5 things that we want to consider when we're putting that system together, you want to identify your runoff sources. So understand that a runoff source doesn't end at a property line. If you got a property that's in a low point of a neighborhood or a belly of a hill, you're going to have to make sure that you calculate all that water that's running down to the area that you're trying to drain. Then you're going to select your methods of capture. So in a yard, typically we use catch basins to collect that water, whereas a driveway or an area of impervious will maybe use a channel drain to collect that water all running in one direction. So from there, once we know where the water is coming from and what we're going to use to capture, we need to determine our peak flows. And then we'll be able to, once we know what the peak flows are, we can size and capture devices and pipe. So these are all things that are very important to put together a system. The last thing that we want to think about is always going to be able to provide a system overflow, whether that is just daylighting a pipe, running it out to a pop-up. These are all things that we want to be thinking about. In the worst case scenario, if that capture device does get overwhelmed, at least that water is going to have somewhere to go at the end of it to get out and make sure that the system doesn't back up. So these are just some examples here of a drainage system anatomy. And guys, if you have any questions or comments, feel free to jump in at any point and I will stop talking so you can ask your questions. Just jump in. You know, I can't see you raising your hand, but if you speak up, I'll hear you.
Yeah, and the other thing, sorry to interrupt you there, Eric. You could type on the group chat if you have any questions as well, and I'll see that and I'll get that across to Eric.
Thanks, Justin.
Yep.
So drainage system anatomy, you want to capture at a point like a catch basin or a channel drain. Filter, we can talk about filters in a catch basin. We talked about those in the common problems solutions last week. And then you're going to convey and infiltrate the water back down to the ground. When we talk about conveyance, we're talking about moving water through a pipe. When we're talking about infiltration, we're talking about storing the water in some sort of a void. What you're seeing here is infiltrations coming via flow wells and easy flow, so that water can leach itself back down into the ground without having to accumulate at the surface. So you can see at the bottom right there, that's got an overflow. So if the water coming off of that driveway, the water coming off of that sidewalk, and the water coming off of that roof via downspout, in a really intense rain event becomes too much for that system, it's going to have an overflow that'll make its way out of it instead of starting to shoot out of the catch basin or the channel drain. So we talk about capture. We're talking about the source, rate, and flow of managed runoff dictates the type, size, and configuration of the capture devices. Surface flows are pulled by gravity and more towards lower areas by following the lay of the land, either directionally or in sheets. Sort of the takeaway from that is make sure you put your catch basin in a low spot of the yard to make sure it's going to collect all that water that's going to be running across it. Subsurface flows are also pulled by gravity, but are affected by soil type and limiting features such as bedrock, clay layers, and structures from like building foundations or retaining walls. Okay, so when we're talking about selecting a capture device, we're talking about directional flow, we're talking about catch basins and grates or pipe inlets. That's where you see that there's a low spot in the yard, you see there's a low spot in an area, and you're going to allow that water to make its way to that low spot where it can then be captured and conveyed, infiltrated someplace else. We're talking about sheet flows, we're talking about driveways, loading docks, sidewalks, where you have a large, consistent sheet of water running across an impervious surface. You don't want, if you put a catch basin in a concrete area, you don't want to have to pitch that concrete in 4 different directions to line up with that catch basin, where you can shoot it all directly towards the garage, put your channel drain right in front of the garage and capture everything at one point. You cover up, 15, 20, 30 foot long, linear foot area by putting a 4, 6, 8, 10-inch channel drain, depending on the amount of water that's going into it. And then we're talking about subsurface flow. We're talking about French drains. We'll get into easy flow. So capture, directional or area drains. You can see here that we've got you've got this home here that we're probably has some low spots around. This is a very common thing when you go out to a job site and you notice water standing in certain areas around the property. Directional drains, also called area drains, are generally basins or pipe inlets placed in low points in the landscape to collect directional drainage. Okay, so when we talk about sizing an area drain, we have to consider what areas are actually running into that. You can see the green highlighted area there of lawn with 2,000 square feet with 600 square feet of roof. So if we're looking to collect the roof and the lawn in one area, we've got to do a calculation for both of these. So we see our roof is 600 square feet of impervious, so the coefficient of runoff is 0.95. And we see the lawn is 2,000 square feet. We're going to consider that to be a loam soil with a coefficient of runoff of 0.35. Next thing that we're going to have to do is select the design storm to determine the rainfall intensity. NDS online calculator or mobile application. So like I said, we will get to this. I can show you how we can play around with that a little bit and plug some things in there. So the roof, based on, this is a home in Parker, Colorado. So the I of the formula CIA, the I is 5.4 inches, a 25-year, 10-minute event. That's going to, we know that the roof is 600 square feet. 32 get, you know, the roof is, pardon me for a second. The roof is 600 square feet. We know that it's 5.4 inches in a 25-year, 10-minute event. From doing that calculation there, we see that we're going to get 32 gallons per minute off of the roof. We're going to get 40 gallons per minute off of the lawn, and the Q, the actual area of both of these, is 72 gallons per minute. Now that we know it's 72 gallons per minute, we know that we can let the water run off of the roof, and directionally throughout the side of that lawn there, that a NDS catch basin will allow you to capture 115 gallons per minute, or even 86 pounds per minute in a speedy basin. So that'll be able to handle that calculated peak flow. Once we know what the peak flow is, we can decide the size of either the channel drain or the catch basin that we're going to need to install to capture the water that's in that area. All right, this is probably a pretty good place to stop. Does anybody have any questions?
I have one. Can I ask? I mean, for some of us that are not good with math or things like this, is these available? So when we're walking a client's home, and can we get NDS to kind of help us with this if we send kind of the numbers, and then can we send this to somebody, or you follow me? What I'm trying to say?
Yeah. Can you guys hear? If I get thrown off here, I'm apologizing ahead of time. I'm going to try to get to my web browser so I can show you how this works on our website. Okay.
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 Yep. Go ahead.
Let's do this. Let's go to. Okay. So if you go to our website here, you're going to come to our homepage. All right. Right here on the contractors, you can go to calculate runoff and system requirements. Push that in there. Drainage calculator. So right here, so we say, let's give an example here of where we're going to use, we have a 2,000 square foot roof, right?
Mm-hmm.
2,000 square foot roof. Our coefficient is going to be concrete asphalt roof. We can choose that. Choose the 25-year rain event. We talked in our area, probably 2 to 2.25 is going to be a good number. Choose 2.25 for the 25-year rainfall. When we have the app up and running again, we could even do a 10-minute course at some point here. It should be up in the next week or two. Once we have that back, I could run it through you with the app as well, because there's a lot more, you can move things around and make a lot more of a detailed calculation, because you can enter multiple square feet drained. There's a lot more to it. But once we know the square feet, the coefficient of runoff, and the design storm, the CIA of the Q equals CIA, you can hit calculate. We know here that 2,000 square feet of roof is in that design storm is going to be 46.77 gallons per minute. That's a very baseline way to come up with that, instead of having to reach out for us and calculate everything. Having this at your fingertips, either on your phone or your iPad when you're out on a job site, will answer a lot of your questions. Does that help out a little bit?
Yes, thank you.
Thank you. All right, let's see here. Okay, so for that same thing, for that 2,000 square foot roof, that's 46.77 gallons per minute. So a 9-inch catch basin and grate is going to handle 115 gallons per minute. So if you're trying to collect the water off of a roof that large, a 9-inch catch basin under the under a downspout is going to more than handle what you're looking for. Any other questions?
Eric, it's Shane with Aquarius.
Hello.
So I see in this example, the 9-inch catch basin will handle that.
Mm-hmm.
How do you determine the size of the pipe that you need as well?
Well, we go to here. Again, this is on, to feel as ill-equipped as I do right now, having to go to you guys without the app in my hand, which answers all of these questions, it's pretty uncomfortable for me, because usually all I do when I teach classes is go to the app. Everybody can see it in front of them and it works great. And I do truly apologize that I don't have that to share with you guys at this point. But if we go again to this drainage calculator, we go back one, drainage pipe calculator.
Ah, gotcha.
Okay, so if you go to here and say, again, 2,000 square feet, concrete, asphalt, 25-year, we go to the 2.25. Slope of drain pipe, let's say you have, we don't have much slope, we got a 2% slope just for giggles here. Submit. You can get away with 3-inch smooth wall PVC or 4-inch corrugated pipe. We'll get into the corrugated versus PVC thing a little bit later in this presentation. But I mean, you can see here, let's say it's a 10,000 square foot roof, just for giggles. And we go back down to here, the 2%, submit. At 10,000 square foot, you're gonna have to jump up to a 6-inch smooth wall to handle that. That gives you an idea of what you actually need to use in terms of a pipe. 4-inch seems to be sort of the standard in southeastern Pennsylvania and most of New Jersey. That's what guys tend to gravitate towards. And 4-inch pipe, we'll get into how much that can actually handle here a little bit later in this presentation. Cool?
So I don't want to get too far into the weeds there, but if that 10,000 square foot roof has multiple downspouts, can you use the smaller pipe just more times? Does that make sense?
Of course, no question.
Okay.
Yeah, absolutely. As long as those pipes are outletting, as long as you're not combining the pipes, you're not going to need to go up. Let's say you split that here. I'll go back to this just to show you this. So let's say
if I had two 4-inch pipes, then that would be fine on that 10,000 square foot.
Well, let's see what a 5,000 square foot roof does. If we're going to split, let's just say we're splitting it in half, right?
Right.
4-inch smooth wall PVC.
Right. Okay.
Anybody else have any questions at this point? Okay. So next one that we're going to get to here is channel or trench drains. So if you're running, you have a sheet flow coming off of an impervious surface. I mean, the perfect example of this is a garage at a low point and the water's running down the driveway. You want to collect the water before it gets into the garage. Same formula applies here. 1,400 square feet of impervious surface. You got to measure out the driveway, in other words. You're going to, your coefficient of runoff is, it's 0.95 because it's an impervious surface. So you have your area and your coefficient right there. And then the only thing you need to plug in here is your design storm. So the difference between a catch basin and a trench drain is, so the Q of this driveway is going to be 125 gallons per minute. Difference is you're going to have to divide that by the amount of feet. So let's say it's 125 gallon per minute and it's a 10-foot drain that you're going to put into. You're going to need, you see here that 12.5 gallons per minute per foot. When we list our grate, the flow rates for our grates, we break those down, and I actually have a spreadsheet I can share with Aquarius that we can send out to the entire group that'll give you the flow rates for all of our grates, so you know exactly the one that you'll need to use in order to get to fulfill that formula. So 12.5 gallons per minute per linear foot on a channel drain. We know that based on referencing what we have, you'll be seeing in this spreadsheet, that a NDS speedy channel with a slotted grate will handle 51 gallons per minute per linear foot, which is more than enough to handle that 12.5 gallons per minute per linear foot that that this system requires. And again, this is something that it's a really simple spreadsheet. It's 4 tables, 4 pages worth of tables just for channel drains and catch basins that'll let you know how much each of those drains are actually going to allow you to get away with.
Hey, Eric, Adam here.
Hey, Adam.
Question on the channel drain. So, like for that one, you know, you designed it so it had the grate could take 51 gallons per minute, but we only needed 12 and a half. So, I mean, I know that there's smaller channel drains, but do you also have to consider what the load capacity is, because you want to be able to drive on this, like on the driveway and, you know, with the load capacity?
Absolutely. And if you're putting a channel drain, and we talked about this the last time, one of the most important things you can do when you're putting in a channel drain is to make sure that it's in concrete. It's very, very important to have some concrete. When you hang a channel drain, when you install a channel drain, you basically want to suspend the thing, either via rebar or like have a few bricks under it just to kind of get it up in the air a little bit so you can get concrete under it and around the sides. That being said, you don't want to put a speedy with a plastic grate in front of your garage. It will not be able to handle that load. So the last sort of factor to consider, and we're getting into this in the next part here, is load rating for driveway applications. Again, we have all that spec information on our website. If you have any question about what a grate can handle or a channel can handle, reach out to me. Reference our website. If you can't find any answers, don't be afraid to pick up the phone. We'll be able to steer you in the right direction. As a general rule, if you're putting in channel drains in front of driveways, I would use our Pro Series channels. We make that the 3-inch, 5-inch, 8-inch, and 12-inch. 3 and 5 are by far the most popular SKUs in that category. They're really, really good at handling that application. You know, we sell those with a plastic and a galvanized grate. So if you're putting a channel drain in front of the garage, 3 and 5-inch Pro Series channel is a terrific way to go. So load rating for driveway applications. You know, on our website, you see these kind of specs right here. If you go on there and search channel drains and find the channel drain you want, I'm going to use a speedy. So I go in there, I pull up speedy. You can pull up all the spec. You guys want me to, can I take a second here to go into the website and show you?
Yep, go ahead.
All right, cool. All right, so if we're going to do that, let's go back to the home page. All right, contractors, specifiers. I would look in specifiers, find technical specifications right there. So if we're looking for channel drain, let's go to grade space and trench channel drains. Okay, let's say we want to talk about a Pro Series channel drain. 3-inch Pro Series, 5-inch Pro Series. So these are the specs for all these. And if you go down to CAD details, so low class AB, which is a foot applicant, you know, basically something where you're not going to have any cars driving over it. Class C is where you start getting into cars. So you see if you're putting this up against asphalt, hit the PDF. And there you're going to see your spec. So 6 inches around the entire thing, around the entire channel drain with concrete, rebar through the rebar clips right there. And then all your questions are answered in this. So depending on any application that you're looking for, the spec information exists on our website where you can easily get to and make sure you put the channel drain in the proper way, especially when you're dealing with vehicular traffic. There's a lot of wiggle room with pedestrian traffic, but if you're putting this thing where people are driving over it, you want to make sure that you're covering yourself. Any questions? Okay. So subsurface drains. French drain is a type of subsurface drain that uses buried pipe to capture and remove adjacent groundwater to prevent saturation. Used in sports field, behind retaining walls, foundations, footings, and more. In fields, the biggest takeaway from subsurface drains is you're managing the water under the surface instead of at the top of it, and you don't have to directionally flow the water to a pipe to convey it out in order to get that drainage that you're looking for. So subsurface drains, French drain in a lawn area. This is the most overbuilt French drain of all time. All this fabric and sock and layers, and this thing is really, really overdone here on the left. A foundation drain at a footing. You can see here, basically it's just creating a void space where water can get into, and then having a pipe in the center that can move that water away. So if you're using our product, then we're talking about easy flow at this point. We'll get into that in a minute. So French drains should be laid out strategically to dewater irregularly poorly drained areas. When you're working with flexible pipe in these areas, you can do like a regular pattern, a gridiron pattern, or a herringbone pattern. Gridiron and herringbone you see a lot on sports fields, soccer fields, inside of baseball diamonds. Even the outfields of drainage is an issue in those areas. So capture subsurface. So another thing to keep in mind here is these patterns include laterals. I look at these sort of systems almost like an irrigation system, where you've got your main and then you've got your laterals that come off your main. You don't want to have too many laterals coming into one main without bumping that system, that pipe size up. So that's something to keep in mind. If you've got 50 to 100 foot runs on that gridiron going, the up and down axis, if they're all 50 to 100 foot runs and you're running them into a main down here at the bottom, you might want to think about bumping that up to a 6-inch to make sure that you can handle the volume that's going to be flowing through that. So here's an example of those layouts: in a regular layout with easy flow, and then an angled gridiron layout with easy flow to get the water out of a backyard. So when you're putting in subsurface drains, you need to keep in mind the soil type. If you're doing a sandy soil, you can get away with putting these things 5-6 feet apart and a foot in the ground, because the water's going to have no problem getting to it. And a clay soil, you want to make sure that you put those laterals closer together and closer to the surface. So if you're putting these in clay soil, I always recommend digging your trenches, and then instead of putting that clay back in top of the trench, to get some nice clean topsoil into that area and allow the water to run through it in a much better fashion. It doesn't have to be like an engineered topsoil, but something from a local distribution that screens a nice topsoil blend to fill in those trenches, allow the water to get through and move through that really difficult clay soil a lot easier. You can see that the amount of space in between these on the clay soil is a lot closer together. As a general rule, I don't recommend burying easy flow any less than 6 inches deep. Only reason I recommend that is because if you run over it with an aerator, you don't want to risk the aerator puncturing the easy flow and making problems for you down the road. So filtration, runoff filtration. So any questions on this part, the easy flow, sort of the basics of that? Okay. So filtration, runoff filtration in the context of stormwater management pursuant to the CWA state and local regulations focusing on pollution control of suspended oil particles and organic and inorganic pollutants like oil and heavy metals. You're going to, the filtration we're going to be worried about on a residential scale underneath the downspouts and in yards is to keep, things like cigarette butts, leaf clippings, trash. You want to keep those things out of your system to keep it clean and have it functioning at a high level for a very long period of time. So filtration of runoff through the drainage system. We talked about this in the last course. We're going to have the basin, your catch basin. The sump at the bottom of the basin is going to allow for some solids to collect down there. Now, if you add in the filter fabric, the filter that we make for our catch basins, it's going to collect a lot more solids before they even get into the system and keep it even cleaner than if you use just the sump alone. Combination of all three is the best way to go. I mean, the grate's going to be your first source of infiltration. The filter, the catch basin filter is going to be your second, and then the sump at the bottom is going to be your third. Conveyance. So when we talk about conveyance in landscaping, we're talking about, we're talking about pipe. So conveyance in a large scale application can be like the Los Angeles River. I mean, it's an armored channel that whole thing is designed to handle stormwater. They're actually jackhammering portions of that up and replacing it with like bioswales and areas for the water to get absorbed back into the ground instead of just running across the concrete and then out into the ocean. So I feel like that's a little bit of an archaic way of dealing with stormwater, and something like that would never be built today. But when we're talking about conveyance and landscape applications, we're 9 times out of 10 talking about plastic pipe. So flexible versus rigid pipe. Flexible pipe's got a lot of advantages. It's easy to bend around. You don't need a million fittings in order to make bends and turn things the way you want them to turn. Anybody here who's ever dug up a job where there was flexible pipe out there before you got onto the site knows what you find in it. They get filled with mud. They get filled with roots. They're not very durable. It's not a very long-term solution. And in terms of moving water, they just don't move water at the same rate that PVC does. If you're not using PVC to do drainage, at least consider it, because the performance of PVC versus flexible pipe is night and day. And we're going to get into that in a table here that we're going to pull up. All right. Another disadvantage with flexible pipe is the fact that if you don't have a dead level trench that you're going to be laying into, you have some undulations in the soil, the water can sit in those low spots, and you may have water that's sort of just accumulating in there and not allowing that system to move the water in the way that it should be. When you sewer and drain pipe, now you're talking about you have a lot more room for error. If the bottom of your trench isn't perfectly flat, that's okay. Basically the drop from one end of the pipe to the other is going to be what's going to make it that water will move through that as long as that trench as a whole is going downhill. So we're talking about minimum pipe slopes for conveyance. So 1 inch is all you really need for smooth wall interior pipe for PVC pipe. So that's 1/8 of a vertical drop per horizontal foot of pipe. That's the only thing you're looking for. We're talking about 2% for corrugated interior pipe. You need a lot more fall to get water to move a corrugated pipe than you do for a smooth wall pipe. So this is a pretty telling table that we have right here. So if we're looking at 4-inch pipe, the second one up going across at a 1-inch pipe, at 1 degree pipe slope, you're going to get 112 gallons per minute they're going to discharge out of a 4-inch versus basically 1/3 out of a, I'm sorry, this is all smooth wall interior pipe, this table here. So 112 gallons per minute is going to go out of a 4-inch pipe at a 1 degree pipe slope. Now, if you go to here, 1 degree pipe slope in a 4-inch, you're only going to get 74. So 112 gallons per minute versus 74 gallons per minute. You can see the big difference that you're using there. And for 3-inch at, a 0.5 or 1%, it's not even recommended at all. The efficiency where that 4-inch pipe moves water versus corrugated is really night and day. And you really see that in the low, when you've got a less of a slope. So when we're sizing pipe for a drainage system, we want to check the peak flow versus the pipe capacity used in the previous channel drain example. 125 gallon per minute is a calculated peak flow running through that example that we used earlier. You know you have 125 gallon per minute running through that entire channel drain. You know the grate's going to work. It's going to be able, a 4-inch pipe at a 2 degree slope is going to be able to handle 157 gallons per minute. Recharging. So any questions on the pipe sizing before we move on to the next section? Okay. So detention and infiltration. So recharging groundwater through stormwater runoff detention and infiltration is the best management practice. We talked about earlier when the difference between an undeveloped and a urban type situation. When you turn a area of woods into a parking lot, they want you to restore the stormwater, the amount of stormwater that's held on that site to the pre-development runoff volumes once construction is complete. The additional runoff volume is created by impermeable surface like roof, parking lots is detained and infiltrated on site. In other words, they want the same amount of water leaving that acreage that you developed. They want that to be the same after development that it was before it. So they want as much of that water to stay on the site as it possibly can. So detention and retention explained. Detention basins are referred to dry ponds, meaning they hold collected water only temporarily after a rain event, slowly releasing collected water or allowing the water to infiltrate into the soil. Retention basins refer to wet ponds, meaning they retain a permanent volume of water that can usually go up and down based on rainfall. Detention retention basins are a combination of the two. That's a permanent volume of water, but have a volume of storage above the permanent water level to detain peak runoff flows while slowly releasing the collected water down to the permanent water level. So I'll give you, here's an example of each. So detention basin is going to be the dry pond. You see these in a lot of shopping center, housing communities. It's a place for the water to go. That water is quickly absorbed into the ground and no water really gets held in that area. A retention basin is a wet pond. So there's always going to be water in that area. If you look to the left-hand side, you'll see an atrium grate that's put in there to, if it really gets going and the water rises above that point, at least it won't get out to the street because the water will be making its way into that atrium grate. So large-scale detention, retention, infiltration. Now, once we get into this, you'll see this golf course here has an area where there may be standing water in that low spot for a good duration of the year. And in intense rain events, that entire area might fill up with water. It can fluctuate throughout the seasons. Now, what they're seeing more in parking lots is underground chamber systems. We do offer chamber solutions. We acquired a company called Storm Chamber in the winter of 2019. We have manufacture an 18, a 34, and a 44-inch tall chamber. If this is something that you're seeing on sites or on plans, I urge you to reach out to me or to Aquarius. We can help you with the design, the sizing, everything. Even if it's spec'd another manufacturer's product, we can walk you through that process to see if we can get our product onto that site and to help you out with those large-scale stormwater needs. So smaller scale stone system, we talked about this with the dry well, typical dry wells. And this is something that we all see where the water comes out, makes its way into the crushed stone and sort of gets back down to the groundwater that way. And we also talked about a trench where the water comes in off of the surface, either is conveyed or just held in that area before it leaches back down into the groundwater as well. So engineered systems compared to stone. So a flow well is going to have 250% more detention volume than an equally sized hole filled with stone. The flow well is completely empty in the center. So any water that makes it into that is going to count as calculated volume of storage. So it's not a percentage like it is when you use a hole filled with stone. Easy flow is 13% more detention volume and 30% better flow through than a stone infiltration trench. It's also a very, very easy system to install because you take gravel out of the equation. So easy flow and flow wells and easy flow connected in a series. Typically on the left of the screen where you can't see would be a downspout. The water will make its way into the flow well. Any overflow coming out of that the flow well can't handle will then make its way through that top pipe and out where it goes into the easy flow and then eventually makes its way to the 4-inch pipe, which will typically be hooked up to some sort of an outlet at the end as an overflow. So flexible and adaptable detention and infiltration footprint. Using flow wells and easy flows together, you create extra volume while also moving the conveying the water in between the flow wells via the easy flow, the way it's set up there. What we want you to take away from this is you can adapt our products to meet the volume and conveyance needs of any project that you're looking for. You'll have a little bit of math to do to come up with that formula. But it's something where once you have the numbers, you can know with certainty that what you're putting into the ground is actually going to work. So a drainage system must have a discharge or overflow location called an outflow or daylight point, where storm water that is not detained or infiltrated ultimately leaves the system. Large scale diameter pipes, you're going to have something like you see here. An armored outfall with limited erosion. You see this, 18-inch pipe here just gushing stormwater and eroding the whole area around it. That's not the application that you want to be installing here for sure. On landscape applications, pop-up emitters work great. One problem that the guys will run into though when they're putting in the pop-ups is they may have too much volume going to one pop-up. I believe our 4-inch pop-up, the flow rate is going to be 40 gallons per minute. I can double check on that as we go along here. When we're answering some questions at the end, I will get you that number. But when in doubt on a large volume of water going through a system, you definitely want to err on the side of caution. Instead of having one at the end, maybe having several pop-ups along the course of that run will give you better peace of mind that the system that you're putting in there is going to be able to handle the outfall that you need. So we can get back to that here in a few minutes. I just want to make sure I get through these last few slides. So here we go. Yeah, 40 gallon per minute on the 4-inch emitters and 88 gallons per minute on a 6-inch emitter. When you're doing your calculations for your grates, how much, what size, when you're figuring out which device you're going to use to capture and how much that grate is going to allow into the system. And then a 4-inch, sorry about that, chaos just broke out in my house. Then you figure out what size pipe you're going to use. You have to make sure that the end of that pipe, that the gallons per minute they're making it out of the emitter is going to match up as well. If you have 120 gallons per minute going through a 4-inch line, you're going to need 3 pop-up emitters to make sure it can handle that volume. So in summary here, we're identifying runoff sources, select methods of capture. We use in a basin or a channel drain to make sure that we make up for that, to capture the water properly. Determine peak flows. We did that via the rational formula, Q equals CIA. Once we know what the actual volume of water that's going into that area, we can then size the capture devices and the pipe. And then we just might make sure that our overflow is going to match up to the size of the pipe that we're using there. All these things are easily figured out based on the numbers that we give you in this, and then to make sure that your system's going to work properly. So design context and consideration we went through, runoff and surface type, design storms, stormwater calculation, system design steps, and then a drainage system anatomy. And that wraps up this system. So I'm going to come back here.